All right, so earlier today, what we looked at was finding speed and velocity. In other words, using the form v equals delta d over t, or delta d over delta t, one or the other. And again, velocity because it's a vector. Now, the thing is that because displacement is a vector, and that's part of how we calculate velocity, that means velocity is a vector. But what we're going to look at, and what else we looked at was that velocity is how much the displacement changes with respect to time. But when we're looking at acceleration, we're going to look at how much the velocity changes with respect to time. And because velocity is a vector, so is acceleration. All right. And so we actually have two formulas for acceleration. They're really actually the same formula, just written differently. And that we have acceleration is equal to your change in velocity divided by time. One way to find out the change in velocity is to take where you started to where you end in your velocity. So we have VF minus VI. So essentially it is the same formula, just written in a little more detail, right? Because again, if you want to find the change in velocity, you look at VF, which is your final velocity, and you subtract it from your VI, which is your initial velocity. All right, so again, as I mentioned earlier, what we're going to look at is a grade 11 question type, and then move into 2 dimensions for what I would say is a grade 12 type question. That's why we're grade 12 class. All right, so this is my first example. Now I shortened it up a little bit because I don't have much room to write. But during a baseball game, it takes a baseball traveling at 32 meters per second, 12 centimeters to stop in a catcher's mitt. All right, what is the ball's acceleration? All right, so we are looking for the ball's acceleration. All right, so I always like writing down my givens. What information do I know? Now, what else do we know? Well, initially this baseball is traveling at 32 meters per second. So that is my VI. And I'm going to say that it is 32 meters per second. What did I use? Let's say to the right. Let's say this baseball is being thrown to the right. Normally I'd specify. I'm not sure why I didn't do that, but normally I do specify the direction. All right. To stop, well, the catcher catches the ball, moves back about 12 centimeters. And so in this case, our VF is 0. Again, when you have a 0 vector, it's the only time you do not need direction. The other thing is, we know that the delta D, the displacement, is that the glove, if the ball hits it, and the ball's moving to the right, the glove also moves to the right, so it is 12 centimeters to the right. All right, now here's something to watch out for when we are doing our equations, is that our VI is in terms of meters per second, but our distance is in centimeters. They must be in the same units, all right? We must have everything roughly in the same units. Now, I'm not talking in terms of our distance being in meters per second. It doesn't work like that. But if our velocity is in terms of meters per second, then our distance must be in meters. And so I'm going to convert this displacement. That centimeter is going to be converted to meters. And again, there are 100 centimeters in a meter. Hopefully you know that. So I divide 12 centimeters by 100 and I get 0.12 meters. All right, so that's just making sure that all our distances are in meters, just like our time has to now be in seconds. All right, so standardize things. Now, here's a problem that we have. I want to use this formula, right, for acceleration, but I'm missing time. I don't have the time here to figure out the acceleration. So this is something that we're going to get into in our next class, is a little review of motion equations. And there is a motion equation that involves delta D and these other variables that we have, VI and VF, that is going to allow us to find the time. And that formula, and again, we're going to reintroduce ourselves to this formula next class. Well, one of the several formulas that there is we have delta D is equal to 1/2 VI plus VF times delta t. All right, so again, we're going to review some of those motion equations, but that's the one we need for now, just kind of introducing it for next class. All right, now I look at all my directions here. I'm going to substitute into my formula. I need to dictate which direction is positive and which one is negative. In this case, because I got right, right, and right, and generally I always make right positive, and I'm going to do that here. So right is positive, which means left is negative. All right, and so when I substitute in my formula here, I have the displacement is 0.12 meters to the right. So I'm going to put a positive 0.12 because it's to the right. When I have a fraction in any equation, fraction is just a divided by question, it's not done yet, so I like to convert it to a decimal. And so I do it there. All right, 0.5. VI to the right, so I'm going to put a positive 32 here. And my VF is 0. And of course, we have my delta T over there. All right, so now, now time to do the math. A little badness here, so I can figure out this right side a little bit more. 32 plus 0 is 32 times a half would be 16 delta T then. All right, so we'd have a half of 32. 16. Again, I want to get delta T by itself, so I'm going to divide both sides by 16. All right, and my delta T is going to be, if I figured it out, again, this happens very quickly, 0.075. And again, because everything, my velocity was in meters per second, my distance was in meters, that's how many seconds it would take for that ball to stop. Obviously, when the ball is coming in at over about 100 miles an hour, it does stop very quickly in a short amount of time. So now I've used, like I said, one of my motion equations that we are going to, again, get into next class. All right, I use one of those. Now I'm going to use, well, another motion equation, which is my acceleration one. All right, so let's see here if I can fit it all in here. So I have my acceleration is equal to VF minus VI divided by delta T. All right, so I sub my values in. Again, I'm saying right is positive, which I generally always do 99% of the time. So I have a 0 is my VF minus VI, which is going to be a positive 32, and divided by my time, which is this very small amount of time, 0.0075. All right, now, again, up top, we have 0 minus 32. Well, that's going to be negative 32 divided by that 0.0075. All right, and now I do a little bit of calculating. I take my minus 32 divided by my 0.0075. Negative divided by a positive is going to be a negative answer. And I'm getting negative 4,277.6. Oh, 77? Nope, 0.66. Negative 4,266.67. And now, again, acceleration is a vector. All right, so I have to express it as such. And so I'm going to have my final answer here that my acceleration, the magnitude is 4,266.67. My units is that we're looking at, again, the rate of change of our velocity with respect to time. So how fast does the velocity change, meters per second? How much does it change every second? And so our units are meters per second per second. So it's meters per second squared. Now, again, acceleration's a vector. This negative sign, I said that right was positive. In this case, I said that that's how the ball was thrown. And so because my acceleration is negative, that means this acceleration is headed left. And that makes sense because if your ball's traveling to the right, the only way to decelerate is to accelerate in the opposite direction. So in real life, we talk about a negative acceleration as decelerating, but in physics, really what's just happening is you're accelerating in the opposite direction. That's what slowing down is all about. All right, so again, this is a straight line problem because this ball is being thrown straight, one dimension. All right. And again, here's one of our motion equations. Actually, here's another that, again, we're going to get into next class. But now we're headed towards acceleration in 2 dimensions. All right. So our next question, where things change up a little bit. A little bit of a trick here. All right. So I'm going to need all this room. So let's get rid of this. Big question, especially when we get to 2 dimensions, as always. All right. All right. So again, I'm just going to do one example or a second example here because, again, I'm going to have to come up with a resultant. And we'll see how that works out. So it works out a little differently with this question. In example 2, hopefully you have it in front of you here, but again, I'll try to put down some of the details. A lawnmower takes 4.5 seconds to travel from point A to point B. What is the average acceleration? All right, so here's the delta t. It says 4.5 seconds. Okay, now there is a diagram on this sheet where there's a velocity, initial velocity called VA, it's called here. And so I'm going to write it down as my initial velocity. And it is 1.8 meters per second. All right, and the direction is 27 degrees south of east. Make sure I get this information down right. All right, there we go. And then it changes its velocity. And so now it has a different velocity of VF. So it's still going the same magnitude, but again, the velocity changes any time that you either change the magnitude or direction. So this lawnmower is still moving at the same speed, I guess, if you will, but in a different direction. And now it is, going at 1.8, 15 degrees east of south, or is it here? East of north. All right, east of north. Make sure I get my information down right. There we go. All right, so I have my initial velocity, I have my final velocity, and I have my delta t. All right, so here's how this one's changing a little bit. We're going to do a lot of the same skills that we did before, but the initial part is a little different. So we'll get to that right now. All right, so my acceleration formula is VF minus VI all over delta t. All right. So now I'm going to substitute into my formula. All right, so I have A is equal to VF, which again, I'm just going to write it down here, 1.8 meters per second, 15 degrees east of north, all right, minus the VI, which, don't need that square bracket yet, which is minus 1.8 meters per second, 27 degrees south of east. All right, and of course, divided by my time, which is my 4.5 seconds. Now, here's how things are different than what we did prior to. We've added vectors, right? We've done that by, again, dismantling the horizontal components of each, putting them together, doing the vertical components, tearing them apart, put them together so that we have the horizontal and vertical components of our resultant, and then putting it together and being able to find the resultant. That was from adding vectors, but here I have a vector subtracting a vector. So there's a little adjustment you have to make here. And we do this with numbers. And what you can have sometimes with numbers is if you have minus positive 4, for instance, a lot of ways, if you subtract 4, another way to look at it is we're adding negative 4. All right, so those are the same thing. You can subtract a positive 4 or you can add a negative 4. The result is the same. I'm going to do that with this and with my 2 vectors. Instead of subtracting the vectors, I'm going to add them, but I got to make an adjustment here. Just like I did with my 4s, instead of subtracting a positive 4, I'm going to add the opposite. All right, I'm going to add the opposite. So now my equation becomes this. A is equal to 1.8 meters per second, 15 degrees east of north. That didn't change. but I'm having trouble with this minus sign. So I'm going to add the opposite, which is 1.8 meters per second. Now, what is the opposite of 27 degrees south of east? Not hard to figure out, because the opposite of north is south, the opposite of east is west, and so the opposite of 27 degrees south of east is 27 degrees north of west. All we do is flip the directions in there. You see a south, put a north, you see an east, we put a west, or vice versa. Now I have two vectors that I can add up. All right. And again, for us, I'm going to use trigonometry. So again, I've got my two vectors, so I'm going to do the same thing I did earlier today. Get the horizontal components, get the vertical components, put them all together. All right, same thing I did. So I go over here for, again, these are not the same. Well, VF is still the same. This VI now is the opposite. It's negative VI. But I'm just going to call this, I'll throw a little 1 over here and a little 2 over here, so I straighten things out. Now, again, because I've done this so much, I'm going to skip a few steps. But again, I'm going to write out most of what I'm doing here. All right, so here's number 1. Vector number 1. Again, I'm going to write a compass rose here. Never enter stinky washrooms. All right, this first vector I'm talking about is east of north. So it is in the east-north quadrant. So again, just as a diagram, there it is. All right, 15 degrees towards the east from the north. So we're going from the north. There's our 15-degree angle right in there. All right, and this has a magnitude of 1.8. And again, let's see here. So there is our vertical component. So I guess I'll call that V1V. So I'm calling that vector 1 right now. And of course, the horizontal going across here would be V1H. All right, so again, my trigonometry, that's again a 15-degree angle. I'm not sure if you can see that on the camera here. Could be a little tough, but again, that's a 15-degree angle there. All right, so which one do I want to do first? Doesn't matter. V1V, it's adjacent, so it's going to be cos. So cos 15 degrees equal to V1V over my hypotenuse, which is 1.8. So that's the magnitude of this vector. All right, so if I, again, cross multiply here, V1V, cos 15 times 1.8. So let's see here. I'm going to need my calculator because I did this on a diagram. So let's see here. So cos 15 times 1.8. I get 1.74. And again, the direction here, we're talking about meters per second. And the direction from what I see is north. All right, V1H, that would be sine, because it's the opposite, 15 degrees equals V1H over my hypotenuse of 1.8. Again, V1V, no, I'm doing V1H. V1H is equal to sine 15 degrees times the 1.8. So we'll try that out now. Sine 15 times 1.8. I'm getting 0.47. Yeah, that makes sense. 0.47 meters per second. And again, I look at the diagram, it is headed east. Perfect. All right. All right, 2 down, or 1 down, 1 to go here. So let's see here. Going on my second vector. All right, which is this one here, the 1.8 meters per second squared, 27 degrees north of west. All right, never enter stinky washrooms. North of west, that means it is in the northwest quadrant. So again, I'll draw a diagram there of my vector. All right, 27 degrees towards the north from the west. So there's my 27 degrees right there. All right, and again, drawing in my vertical components of my second vector. All right, so, well, we'll draw the horizontal line first. We'll go this way. There's my V2H. Go up. There's my V2V. All right, and again, the magnitude is 1.8 here. All right, now again, trigonometry. This time V2V is the opposite. So V2V is the opposite, so I'm going to use sine. So it's, again, I'm going to go a little quicker here. So V2V is equal to 1.8, our hypotenuse, times the opposite. So it's going to be sine 27 degrees. All right, and V2V, let me see, I got to figure that out here. So sine 27 degrees. Again, just repeating what I've been doing. I'm getting 0.82. Again, 0.82 meters per second. Which way are we headed here? Upwards, north. Okay. All right, and then again, I'm going to do V2H. Let's see. It is cosine we're going to use because it's the adjacent, so it's going to be the hypotenuse times that cos 27 degrees. V2H. We're getting as, let's see here, cos 27. Okay, times 1.8. 1.6 meters per second. And let's see, which way are we headed this time? It's headed to the west. All right. There we go. So I've got all my components. I've taken those two vectors, I've ripped them apart. Now I'm constructing the resultant vector. All right. So again, I'm going to do some addition of vectors here to get my resultant. So again, when I add these two vectors, I'm going to call it VR, the resultant. All right. So I guess I'll find the resultant horizontal component first. And so I look at my two vectors. I have a vertical component of going north and a vertical component going north. All right, so I'm just going to add those two, and then my direction will be north. So I got the 1.74 is one vertical component. The other one is the 0.82. And I get 2.56 meters per second. And again, it's north. All right, I find the horizontal component of my resultant. Again, I'm constructing my resultant here. And let's see, I got one going east, and one going west. Okay. All right, so those are going to be subtracted because they're in the opposite direction. One's east and one's west. All right, so so I figure that out. The west is the big one, so we're going to be headed west here. And in fact, I get 1.13 meters per second west. All right. So we're still a little bit here. We're trying to get back to this equation here, but now I'm going to put these two together and find out my resultant. All right. Both the magnitude and direction. And so let's see here. We have, where am I going to draw this? I'm going to go up here, I guess, to put my resultant together. So let's see here. We're going to need that equation. All right, so up here we're doing the resultant. All right, so let's go with a different color. All right, so first off, drawing this out. So there's my compass rose here. Right, never enter stinky washrooms. This thing's going 2.56 to the north. There's 2.56 right there. All right, and then the next one's going west, 1.3. 1.13, pardon me. All right, and our resultant will be, I guess I'll draw it in a nice green line here. There's our resultant vector we're looking for. And we're going to need that angle as well. All right, so again, I'm going to use the cosine law, or not the cosine law, sorry, the Pythagorean theorem. So there's my VR there, my resultant vector, putting these two guys together. All right, so the magnitude of VR, size of it, I'm going to take 1.13 squared plus 2.56 squared. All right, so I'll use the Pythagorean theorem there. And what do I end up with here? Let's see. Take that 1.13 squared. There it is, 1.28. All right, and let's see here. I'm getting 2.8. All right, so we get a 2.8 is my magnitude. All right, now I look at direction. Again, I'm going to use trigonometry here. I want this angle here theta, so I got the opposite and the adjacent. So we got tan theta is equal to opposite, the 1.13 here, divided by the 2.56. All right, and my angle, let's see, what do we get here? So again, use my calculator. So we got to go 1.13 divided by 2.56. And then I use tangent inverse. Figure what I got. And my angle is 23.82. All right, 23.82. All right, so now, as we've done before, I rip my two vectors apart into their components, combine those components to put them together to get my resultant, which I'm going to write in here now because now I can finally go back to this equation, right? I've got A is equal to, well, I just added these two vectors together. We got 2.8 meters per second. The angle here is 23.82 degrees. And if I look at my diagram, towards the west from the north, so it's going to be west of north. All right, and again, I'm going to have to divide it by my 4.5 seconds because that is just the adding these two velocity vectors up here. All right, and then finally, I take 2.8 and I divide it by 4.5. What do we get here? 2.8 divided by 4.5, and I get 0.62 meters, and again, acceleration is meters per second squared, and of course the angle is 23, that's not going to change here, 0.82 degrees west of north. Or as I mentioned, just like any vector, whether it is a velocity vector, displacement vector, acceleration vector, can be written as two ways. So this could have been 0.62 meters per second squared. Let's see, I'm going to subtract 9 that angle here, 23.82 from 90 degrees. And I get 66.18 degrees, which would be north of west. In other words, it would be this angle right in here. Because again, you can describe your vectors as two ways. In this case, I described it leaving from the north and leaving from the west, both ways. But again, there's a little bit of a difference there where we had subtracting two vectors, putting them together. You don't learn to subtract vectors until you get to calculus. And again, you can probably use diagrams there. But what we had to do, the trick of it all here was to add the opposite. When you're subtracting two vectors, the easiest thing to do is add the opposite because we've been adding vectors, again, with displacement, with velocity, and now here with acceleration. All right, so that is it for today.